So we have Romain with what's new in BifurcationKit.jl. Take it away.
Thank you very much. So it's a very great pleasure to be here today. It's my first JuliaCon, but I've been working on using Julia since 0.3 or 4. So I'm glad to see to put faces on all these names I've seen on Slack or whatever. So today, of course, it's what's new with BifurcationKit. I've been presenting this 2 or 3 years ago, so hope there have been a lot happening since then. But I will focus on computing curves of bifurcation of periodic orbits and their co-dimension to bifurcations. Okay, so don't worry about it. This is the very latest addition to the software, and you will see that's a very practical problem. So the outline of the talk is I will present very briefly what is bifurcation theory, so that people who doesn't know it don't get lost. And people who does know it will be bored. Computing periodic orbits. So you see what are the different methods that are used in the package to compute periodic orbits. So this is the math part. You know, it's in blue. And then we will switch to the new API of BifurcationKit and the consequences of it. And then I'll break my number 1 rule, which is not to make real-time simulations, but for you, I will break it. And we'll put into action this goal of computing curve of bifurcation. I'll show you how it can be very useful. And then we will conclude. So let's move to the first part, which is, let's say, a few words about bifurcation theory. In a nutshell, it's to study equilibria and periodic orbits of ODE. In BifurcationKit, n can be millions. And if you look for, equilibria, which are points solution of the ODE that do not evolve in time, so these guys here, they are these equilibria are basically the zeros of F. Okay, so as an you also can compute zeros of vector field as a byproduct of these tools. Okay, of the tools I will present. So now the question is, those equilibria are stable or not dynamically? And so the mathematical result is basically that the point here is a bifurcation. So for a specific value, Pbif is a bifurcation point if there is an eigenvalue of the Jacobian with a 0 real part. So why is that? Because usually when you have this, you have a change of stability of the equilibria. So for example, you will give birth to oscillations. Or you have a new local branch of equilibria nearby. So here on the video, I did this for you. You have a parameter here, x here, and in bold, this wide line is the stable part, or all the real part of the eigenvalues are negative. Here it's unstable, so we have at least one eigenvalue with real part positive, and so here, when you cross, you have a 0 real part, so that's a bifurcation point. Okay, so it's a fault in this case. So it's a practical example of what this slide means. So of course we can do the same. We can do the same for periodic orbits as function of a parameter. And of course, if we can solve the right eigenvalue problem, we have the same kind of results, meaning that if we have a 0 real part eigenvalue, it means that we have, I'm simplifying things, but it means that we have a bifurcation, so a change of stability or new branch of local orbits. Again, we have an example here on the right. So here you have the object. This is a periodic orbit. Okay, so paired 6 in this case, and we can follow it along the branch, and you will see you see here. These are the Floquet coefficients. We have something with 0 real part here, so it means we have a bifurcation. So up just after. We have these green dots, the pair doubling in this case. And so you see that's quite similar to equilibria in this case. Okay, so now a very simple example with a Stuart-Landau oscillator. We consider this 2-dimensional ODE. Z dot equals Z times this scalar thing. And so when P is negative, we have obviously the equilibria Z equals 0, which is solution. It's attracting the solution. You see all the flow is going to it. It's because when z is close to 0, the dynamics is basically linear. It's z dot equal z times p plus omega. As p is negative, it converges exponentially fast to 0. If you put p positive, then now the equilibria is repulsive, and you see that the dynamics around, is expelled, and it converges to this circle of solution, which is a periodic solution. Okay, so that's basically the Hopf bifurcation, where you go from damped oscillations to true periodic motion. So this was the math, but numerically, how do we do this? But we continue the zeros of a function as a function of a parameter, p. We compute the equilibria, so we compute the spectrum of the Jacobian. We detect when we have a bifurcation, meaning that we detect the unstable eigenvalues, the number of them. If we have a 0 eigenvalue, it means that nearby there must be new branches. So for example, here in this case, I'm following the pink one. Here I have a bifurcation, so I have a branch around. In the case where the eigenvalue is imaginary, purely imaginary, it's the Hopf bifurcation. We just saw it, previous slide. And once we've detected this, we can branch to the new solution and go back to 1, detect all this, and then you can end up with this zoo of branches, which is for the 1D Swift-Hohenberg PD problem. Okay. So that's for the math. Now let's the first part of bifurcation theory. Now we will review the 3 different ways in which periodic orbits are computed in the package. The first one, and the first one I programmed, it's called the trapezoid method. Very simple. So what we do is we look for periodic solution. So periodic solution of the Cauchy of the ODE. So up to a change of time, we can still assume that the period is 1, but then the period of the solution is multiplied by the vector field. So this is the form that we use. Okay, so there are 2 unknowns actually. We need to know the orbit, the shape of the circle somehow, and we need to know the period. Okay, so these are the 2 unknowns that we are looking for. And what we do is basically we discretize the circle, so x0, xt over m, x2t over m up to x1, and the period. So that's our unknowns. So there are many, if m, the number of slices, is large. And then we discretize E. So very briefly, you recognize here the time derivative. Okay, this is the part. And then we have this minus the h is t over m. So we have t over m. And because we have a trapezoid method, we have half of the mean of these 2 neighbors' slices. Here we have the periodic boundary condition. So that's this one. And then we have a phase condition because every translated version of a periodic orbit is another one. So if we have a non-singular problem, we need to add this. And so on the right, this is the example I was showing you a few slides ago. So this code is very optimized. The radius allocation. With radius allocation, we have 7 different solvers for PDEs. So you can choose how to solve the linear problem. It runs on GPU. We can automatically branch from Hopf bifurcation and the bifurcation of periodic orbits. Here you have a automatic branching from the Hopf point, which is in red. Another way is to look at the flow. So sorry, I forgot to mention the previous method works for intermediate number of unknowns, say 10,000. Okay, you have 10,000 unknowns, you can still use it. For this one, we have basically no limit in the number of unknowns. And it's a different way to compute periodic orbits. Is basically we look at the flow, and once the flow hits the same point again, okay, if we have a fixed point, so x0 and a certain t, then we have a periodic orbit. Okay, so we just look for x0 and t. And so you have an example on the right, which is for a PD called the brusellator. You can see here we have 500 unknowns, and it computes this relatively easily. So they are different, again, because we want to handle ODE, PDE, non-local problem. We have different solvers that are implemented. You can define your own flow, okay? Or you can use wrappers to differential equation.jl. That's already provided in the library. It runs on GPU. You can branch automatically from Hopf bifurcation, pair doubling, bifurcation of limit cycle automatically. From probably 2 months ago, I added the normal form for paired doubling and Nemax-Acker bifurcations. It's a bit technical, but this is basic. There are 2 softwares that can do that now, MatCont and this one. So it's very, very robust tool. This tool is very robust. Standard shooting, I mean. Finally, the last one, and it's relatively recent addition. It's collocation method with parameters n, TST, so which is the number of time step, and a collocation number m. So very quickly, we look for periodic solution xt as before, solution of this ODE in rescale time. And so we start by basically meshing the time. So these are the mesh points. They are tau1, tau n t plus 1. Sort of they are roughly, they are NST mesh points. And they can be adapted. They can be changed, okay, depending on the solution. And on each small interval, so tau j plus 1, we do an affine transform so that we can assume that we can rescale this time interval to -1 and 1. And then we rescale the problem, the ODE, in this interval. So now I have this, I have changed a bit the period on this multiplicative factor. And on each one, each xj is going to be approximated by a polynomial of size m, of degree m. Okay, a Lagrange polynomial. So that's the basics of the method. And you can see it here in use. For example, I will stop. You can see that here we have a nice, relatively cosine-like periodic orbits. And as the parameter is increased, it converges to a periodic orbit with a long period, here already 40. And then we go to 150. And you can see that the mesh is being adapted to capture this homoclinic orbit, which is for those who doesn't know, somehow a periodic orbit of infinite period. So this is state-of-the-art method for ODE. So it's used by Auto, MatCont, Coco. It's very precise. You can do mesh adaptation as I show. And it's been improved a lot in the past 6 months in BifurcationKit. So it's non-allocating. The Jacobian is really is analytical. We have a dedicated linear solver, which is about 5 times faster than what it compared to the backslash operator. Sparse Jacobian-free methods to use for PD. And again, you can do branching from Hopf, pair doubling, and bifurcation of the limit cycle or automatically. And this is basically the only software with MatCont which can do these pair doubling and Nemax-Acker normal forms. Okay, so that's it for the math, and now I'll go into more detail into the library. And so, what is BifurcationKit? Finally, if you didn't know, it's after 10 minutes. It's basically a library for numerical bifurcation analysis of, at first, large dimensional equations. Okay. Here is a quick example of how you can, let's say, look for a compute a bifurcation diagram. For example, here you give a vector field, which is here a cubic. You give parameters. So here we have 2 parameters, but we only use a p in the vector field. We define a bifurcation problem where we give the vector field, initial condition, parameters, which parameter we want to continue with. So in this case, p. And then we call continuation with a continuation procedure, which is pseudo arc length in this case. So this PALC is a bit like the ODE times taper in the SciML framework. Okay, so that's the new API. Okay, the old one, we were basically giving everything to continuation, and it was a mess in the code. Very difficult to dispatch on the objects or to build a very big library. So that was a massive change into the library, but it allowed a very big expansion in the capabilities. And now we have an organization. I'll show you if you don't know about this. There's an organization where we have different plugins. So for example, we have a plugin for delay differential equations. So if you don't know what they are, I'll show you up. So these are equations like this, which depend on a delay. So usually they give a lot of rhythms and periodic orbits. We have also a very recent addition is computing homoclinic orbits. We can also couple with grid app. So it's very nice. So to compute solution of PDEs with using finite element method from grid app, and you can define a grid app bifurcation problem and do the continuation and the bifurcation diagram using basically the same method names as in BifurcationKit. And the last addition is a generalization of continuation in 2 parameters. So now we can continue surfaces in 2 parameters where the z-axis can be very large dimensional. Okay. So the API consequences are basically problem can be automatically created. The solver, linear solver, eigensolvers, they can be tailored using dispatch. We can use very more sophisticated libraries, so compute periodic orbit with 4 methods. I presented 3, but there are 4 methods, and the solvers are dispatched on the type of these on the type of the method used for defining periodic orbits, and so on and so forth. One last thing that is very useful is the result encapsulate everything that is needed to rerun the computation. So for example, in this case, it's a branch of periodic orbit, and the algorithm, you can see that it's a pseudo arc length continuation, and you know something about flow K coefficient has been inserted into the... So it's been automatically created, and it's saved into the branch. Same for the problem. It's a bit like the SciML solution type of... so everything is recorded in the branch. You don't lose anything, okay? You can rerun it just from that. So now we have... if we compare to other software in the field, we are very close to MatCont in terms of functionalities. We share a lot of functionalities with MatCont. But there are a few things that we are very different. So for example, we can monitor function along the curves. So that's very, basically MatCont and BifurcationKit can do it, and Auto also. For periodic orbits, we have many methods, and the use of the fact that we have many methods to compute periodic orbits is because we can tackle very large problem or very small problem with more precision. So you have the choice for that. Otherwise, you're stuck with a small problem with the other frameworks. I won't enter into the details, and the blue box is about periodic orbits. And what is missing compared to, let's say, MatCont is we don't have a very high-dimensional bifurcation of periodic orbits, which are embedded into the BifurcationKit. But to me, one very important thing is we have testing in BifurcationKit, a lot of testing. So the CI is more than 1 hour to test that the results are right, right? You can trust the result. In Auto, we have a bit of testing, but it's more about that there's no bug, that the functions run. And we have not discussed branching or, let's say, large dimensional case. Okay, that would be another way to compare the different frameworks, strength and weakness. So let's, after this very general overview of the recent addition, I would like to give you a practical example of how to use it in real time. We look at this, this complex equation. We don't really care what it is. It's just that it is complex enough to provide interesting dynamics, okay? And so here we have a bifurcation diagram that is produced, and I hope I can do that like this. Yeah. Plus, everybody can read, I hope. Is it large enough or? Okay. Thank you. So here the vector field is programmed, is already derived. I take an initial condition, which is the 0, the equilibria I want to compute, okay, to follow. So as I told you, we define a bifurcation problem like this. So I put the vector field, the initial condition, the parameters, which are all this named tuple. I want to continue with the parameter k8. Why not? I want to continue between minus 0.1 to 20. And then we continue it. It's computing the branch. the plot is on the right. We have a half bifurcation here, another one here, and a blue one. And they are given in the, so if I type BR here, the result, I see that I have basically information about the bifurcation point that have been shown. So what does it mean practically? For example, if I go here, just after the red dot, the equilibrium is stable. So we can simulate it here. So after the bifurcation point is the bifurcation point plus something. So I do that, and you see nothing changes much. It converges to a different equilibrium, but which is nearby. So if I go before the bifurcation point, in this case, I see oscillations. Okay, so that's what I told you before with the Stuart-Landau oscillator and so on and so forth. If I compute the normal form of, I think it's BR2. Yeah. So here on the right, it tells you that we have a half bifurcation and the period is about 11. Okay, so if I zoom in on, I should be able to see 11 here. But we can do something more interesting. We can compute the periodic orbit. So what we do here is, I want to branch from the second point, which is a hop, and I'm going to use collocation with 50 time step and collocation order 3. Okay, so let's run this. It's compiling. I hope it's not going to crash. It would be a disaster. Okay, we got it. So we have a branch coming out, you see, and we have seen different bifurcation points along these things. So here we have an orange one, which is interesting, which is an Emacs sucker. So for those who doesn't know, we'll play the game again and simulate the dynamics after. So before, sorry. So it should be, yeah, that's it. And we see nice oscillations before the Emacs sucker bifurcation. And if we go after, hop, what we will see are, you see breathers like this. So like we have two oscillations, two frequencies into the dynamics. So we have the first dynamics. So let's have a look at the normal form. And so if we compute it, it tells us that basically the underlying frequency is 15 and the other one is about 100. Okay, so this is nicely predicted. So now the thing we want to do is, so that explains this diagram here for you, hopefully. But if I change the parameter K7, for example, it will, and we run all these simulations, so all these branches, you see the bifurcation point will vary a bit, okay? But this is very troublesome. And if I put it on top, so if I look at the same plot but from the top, here I see those bifurcations. So I know here I have oscillations. In this area here I have torus solutions, and here I have no oscillations. So there should be a way to jump from this point to this point automatically without computing everything else. Okay? So of course there is a way, and that's called the curve of bifurcations of periodic orbits, the big word but simple concept. And here you can see that we can compute the curve of Emacs sucker. They are like this, and we can detect higher codimension, so Chancinet bifurcation in this case, and here you have the fold. Okay, so that's basically the last big addition to the software. And it's the numerical method I explained in the doc. I will be a bit quicker now. One last thing. Yeah, to compute this normal form, there's no analytical formula. So it's been tested against approxFun. And to my knowledge, this is the only software where these normal form have been tested. Recent improvement is we can do the same with two parameters. So we can compute periodic orbits. These are periodic orbits here. And you can, with two parameters, so you can see the same on the right. So it's very useful to find isola, for example. We have also improved a lot the linear solver of collocation. So the solve goes to 3 milliseconds, in this particular example, to 300 microseconds. So it's almost a factor 10. So this is a method that is used in auto. And that's it. And I want to conclude now to give time for questions. So in conclusion, the state of numerical bifurcation analysis is well advanced in bifurcation kits, at least for ODE. And to my knowledge, there is not much to do. To go for higher codimension would be meaningless. Nobody does it, and there's very little use for that. Okay, so this is basically feature-full roughly speaking, in this direction. There are many solvers available. For example, the last solver I was mentioning, which is faster, should be useful to SciML as well. They are Jacobian free. I'm not sure that all of what I presented today works on GPU. Should be in principle. We could do the same for delay differential equations, but that's in red, so it's a massive work. If you want to help, an interesting thing would be to make a GUI out of this method. That would be very useful, I think. Or you can, so it's in orange because it's a bit of work. Simple and useful help with the issues or provide feedback on the API. You don't like the way it's framed. This is very useful to us. Something very difficult is integration with nonlinear solve and linear solve. Right now we rely on a custom linear solver that are from CryLoveKit and so on and so forth, but Newton is very simple. And that will solve probably the problem of in-place and out-of-place method in the library. Complete a full integration with readapp that I mentioned. So basically half of the library is linked with readapp, and I think that would be very nice. Distributed computed. That would be a nice way also to improve the library. I don't know if it's simple. Simplify the integration with dynamical system by George Datseris. I think that would be very nice too. The integration with Modeling Toolkit has been done, more or less, I would say, thanks to Torkel and Romain, and this is very nice. You can just, it's very nice framework. I would like to do the same with method of lines and etc. And with this, I will thank you for your attention and take any question if you have any.
Thank you, Romain. Any questions? Hands up.
Hi, really nice talk.
Thank you.
I understand you have 3 or 4 methods for continuation of periodic orbits if you branch from a codimension 1 bifurcation, but from a codimension 2, which methods are available?
The same. But
the same, exactly the same.
But for the dimension 2, so it's you cannot change. So if you've computed using collocation here, you cannot change to compute this one.
Okay.
I mean, that would be doable, but yeah. But that's a lot of work.
Okay.
Yeah, thank you for the...
Thanks a lot for the talk. I have a question about the very, very last part, the ... What about difference equations?
You mean discrete time dynamics?
Yeah.
I have 2 hands only. There's a beginning of it in the code. It's a bit hidden because to compute normal form and bifurcation of in the shooting case, it's basically a Poincaré return map. So it's discrete time dynamics. So Neymark-Sacker bifurcation, what else? Period doubling, they are already encoded. And the detection of these bifurcations, which is a bit different from the continuous time dynamics, is already coded. So I think what is, at least for code dimension 1, what is missing is an API, which takes this thing. Of course, for codim 2, you need to program it. Yeah, I mean, for example, I don't know, Chancinet is already programmed. So yeah, some of the tools are already present, but they are not outsourced for the user, I would say.
Okay. Is that something that can be expected sometime?
If you open an issue and if you want to help, I can guide. Yeah. Is it okay for you? Yeah.
One short final question.
Short one.
But it's not easy, huh?
At what extent do you use automatic differentiation, for instance, in your continuation methods and so on to create Jacobians? And what are maybe possible open questions in these directions?
I'm not sure I understood. You want to know if I use AD for the Jacobians?
Yeah.
So, right, the default now is forward diff, and it's dense Jacobians. But you can pass your Jacobian in the bifurcation problem. You can pass your own. I think it would be nice to use abstract differentiation so that the user can choose the framework. And for periodic orbits, there's a mix because I want it to be fast, non-allocating, sparse, and so on and so forth. So they are coded in. So there's a mix of AG and analytical formula, or sometimes it's a full analytical formula. Yeah, it's very optimized for that. Does it answer your question?
Yep. Okay.
Right. Thank you.
Thank you.
Applause.